Hello everyone, this is Mike Dowding with the SD Mines Physics Department, continuing our discussion on Chapter 27 material. And today we're going to go over some examples of multi-loop circuits. And before we get into that, we do have one definition that we need to go over, which is the definition of the electromotive force. Or EMF for short. And what the electromotive force is it is something which could be similar to a battery, but it is what provides us with a constant or uniform current. So in the case of a battery, your electrochemical batteries, those can provide a pretty stable flow of current. And so if we take a battery of potential V, hook it up to a resistor, by Ohm's law, V equals IR, the current that flows out of the battery will then be the ratio of the two values. And so what we want to do is figure out what other sources of current can we use besides a battery. And there's nothing wrong with using a battery, but the battery is probably going to have a very limited amount of charge, and so there will be a limited amount of time in which we can use it. And so are there other sources of basically electricity? And for that, really what we need is a means of collection. We need some way of collecting charge and then storing it so that we can release it and use it later. And that's exactly what a battery does. But there are plenty of other means of doing that. There are hydroelectric plants, which can provide charge to us. There are windmills. There are wave turbines. Let's see, what else is there? We could have a geothermal plant. So geothermal is definitely a source of energy. That energy can be converted into some kind of an electrical source. Other possibilities would be solar panels. So we could use solar cells to collect energy, convert it to electricity for use at a later time. There is nuclear. And of all of these examples that I've listed here so far, all but one of them share something in common. Whether it's the hydroelectric or the windmill or the wave turbine or the geothermal or the nuclear. So the one that I left out there was the solar. Let's just go ahead and remove solar there for a moment. But all of these methods that we use for energy collection really boil down to one basic idea, which is a spinning wheel. We're going to take some kind of external energy source, and that external energy is typically in the form of kinetic energy. Could be thermal energy. But we're going to use these energies to spin the wheel. And then typically we'll have something like a wire brush hooked up that is just very, very lightly scraping against the wheel. And what happens is when this wheel turns, that brushing effect creates just a little bit of friction, but it is enough to start stripping electrons from the surface, and we connect a wire, we can start collecting those electrons. And then we can start storing those electrons in some kind of battery device, or maybe it's a set of capacitors. But every one of these sources that we just mentioned there are basically just different versions of a spinning wheel or a turbine. Hence the wave turbine, which is one form. But you know, windmills, they have turbines, they turn. Hydroelectric dams, we build a dam to dam up water in a reservoir to increase potential energy. We then use that potential energy to force water through a turbine, which spins and then generates the electricity. With the geothermal, typically what you do is you find a thermal hotspot somewhere on the earth, dump some water down in there, water turns to steam, and you use the steam to turn the turbine. Likewise with nuclear. Nuclear plants are really just very, very complex steam turbines. We use a very hot radioactive source to heat water that then goes through a system of turbines, generates the electricity. And so the one type that didn't go into this grouping was solar, and the solar cells work off of a completely different idea than the spinning wheel. But you know, we've got quite a few choices here as to what we want to use for the source of our electric current. We could even put like a gas generator in here. So we'll fill the gap here with a gas generator. And with the gas generator, what you're doing is taking potential energy of the gasoline, releasing that through a chemical reaction, and then there's some kind of a spinning wheel apparatus that will help to generate the electricity that you need. So out of all of these different means of producing electricity, so I'm even going to include the solar in there. Let's think ahead a few years, or even we can think back a few years to things like deep space probes, like the Voyager series. And those probes have to have some kind of onboard energy source so that they can continue doing their job and transmitting back. And so which of these sources do you think it is? And we can go through the list pretty quickly. Obviously hydroelectric is not going to work because we don't have the water cycle occurring out in deep space. We don't even have the water available. Windmills, there's no air out in space. I guess you could argue solar winds, but I don't know that you're going to get enough momentum out there to drive a turbine. Wave turbines, so these work under the principle of waves in the ocean pushing a turbine back and forth. So again, we don't have that out there. Geothermal's out because we're not on the Earth anymore. A gas generator, we could put fuel onto the probe, but those fuels need oxygen to combust, and there's no oxygen out there in deep space, so that's not going to work. So that brings us down to the last two, and we said, well, nuclear, you know, we use nuclear to drive steam engines, basically. I don't know that we'd want to put water on a deep space probe. We can end up losing it, or it could freeze. But so solar seems to be the last resort for anything that we want to send out in space, really, except that when you're in outer space and you start getting further and further away from the sun, your light exposure becomes less and less the further out you travel. And that operates on the inverse squares principle. So whatever light that we experience here on Earth, if we were to travel out to, say, Mars, which is about twice as far away, we would only get about a fourth of the light exposure that we do here on Earth. And this effect just keeps getting worse and worse the further out you go. And so these deep space probes that we use, they're not going to be able to rely on solar panels, because as we get really far out there to, say, the orbits of Neptune, Pluto, the Oort cloud, our sun is just going to look like every other star. So solar's out. Well, what's left? Obviously, we've had probes that have been sent out there since, the 70s. What did they use? Well, they did use nuclear, but they used it in a slightly different fashion. They used what are called radiothermal isotopes, which are, again, very, very hot reactive nuclear sources, but then they combine the radioactive decay of these materials with something similar to a solar panel that catches the particles that are being released by the isotope, and then that can be used and converted into electricity. And if you've ever seen the movie The Martian with Matt Damon, there's a scene where he goes out and he digs up this radioactive object, and it's very hot, and that right there was a radiothermal isotope that they were using for a power source. Okay, so we have all of these different sources that we can use to provide us with electrical current, and that means that up here where we have our battery, it's at this point in the chapter that we are going to start substituting V for E, because we don't have to rely on just a battery anymore. We can, we could plug this circuit into the wall, and then where is the wall getting its electricity from? Well, it could be any of these sources, really. So long story short, we're not going to see V written in our circuit expressions anymore. We're going to see it written as E. But our electromotive force, it's a battery, it's a generator, it's still providing voltage. So we're going to treat this exactly the same way that we've been treating V in all of our expressions. And so I could just as easily rewrite Ohm's law using the EMF symbol as opposed to V for voltage. So a minor change, and now that we have that idea taken care of, we can jump into the real material for this video, which is a multi-loop. So what I'm going to do is I'm going to put an EMF into our circuit, and we'll just call that E. We have a couple of resistors in here, say R1, R2, R3. And if I gave you some values for R1, R2, R3, along with the value of the EMF, say 100 volts. Excuse me. We really wouldn't have any problem solving for any of the values in this circuit because we've already seen examples like this. We'll put 45 here. But I promised you a multi-loop, and right now this is just a single loop. So to make multiple loops, what I have to do is add more stuff to the circuit. So I'll continue. I'll put in a couple more resistors, and then over here, just to make life interesting, I'm going to put in another EMF source. So now we have two EMFs, EMF 1, EMF 2. We'll let EMF 1 be the 100 volts, and then EMF 2, we'll let that be 50. And since we have a couple more resistors here, we'll call these resistor 4 and resistor 5. And we'll put some values in for those. We'll say 5 ohms, and resistor 5 is, what should we make that? How about 30? So given the two values of the EMFs and the values of the resistors, I want to know everything that there is to know about this circuit. And when I say that, what I'm really referring to is in addition to the resistance values of each resistor, I want to know how much current is passing through each resistor. That'll be in amps. I also want to know what the potential difference is across each resistor, and that will be in volts. And if I can find those values, if I can find all the individual values for current and potential for all of my resistors, then I can answer any question that's posed about this circuit. Now, the last time I drew a table like this, we were going through a different circuit problem, and we solved that by collapsing the circuit into what we called an equivalent. So we replaced all of the resistors in the circuit with one resistor that would do the same job as the rest of them. So can something like that be done here? And keep in mind that the one major change that has happened is that we've included an extra voltage source. We have essentially two batteries in this picture. And if we look at what's happening, I'll switch over to red here. So far, we know how to combine resistors in series, and we know how to combine them in parallel. So do we have anything in this picture that matches one of those definitions? And you might think, well, maybe R1, R2, and R3 are in series. They are connected one after another, but we also have other stuff that is connected in between. And so the definition of series does not hold up. So what about parallel? Well, it looks like resistor 1 and resistor 3 are in parallel, but to meet the condition of being connected in parallel, the heads and the tails of the resistors have to be connected together. And well, right here I've got an EMF in the way, and over here I've got a resistor in the way, so I don't meet the condition of parallel either. Oops. Didn't want to erase all of that. Whoa. So I can't really use either of my equivalent resistor approaches. I need something else. And that something else is going to be our multi-loop approach. I have essentially two closed loops in this picture. We have a loop on the left-hand side, which, as we can see, goes around in a circle, and we've got another loop over here on the right-hand side that goes around in a circle. And so can we set up some kind of mathematical expression to relate to those two sides of the circuit? And I'll refresh your memory. Let's go back to just a single loop, and we'll call this RA and RB. Now we know from previous discussions that if I want to go from one side of the battery to another, I get the potential of the battery. But I don't have to go across the battery. I could go the long way around and still account for the same potential difference. That idea is what we're going to use in the top circuit. I have one path through the left-hand loop, and I have a path through the right-hand loop. And if I can account for the potential difference through each one of those loops, then I can start producing equations, and those equations are going to allow me to start solving for things. So we have a rule that goes with this, and like most rules and laws in science classes, they're named after people. And this one is what we call Kirchoff's law. And Kirchoff's law says that the summation of potentials we'll say along a closed loop equals 0. Now at this point you're probably saying, well, we've gone through closed loops before, and well, they never added up to 0. They always added up to the potential across the battery. So allow me to explain what Kirchoff's law is telling us. Let's say we start at the top of this battery and we go through this left-hand loop. So I would have to add up the potential of the first resistor, the potential of the second resistor, the potential of the third resistor, and all of that would have to equal the potential of EMF number 1. And you're probably thinking, well, EMF number 1 doesn't equal 0. So why does Kirchoff's law say that? Well, because we have not yet completed the loop. If we're going to complete a closed loop, then we have to continue on to the original starting point. So we actually need to pass through that battery and get back to our original starting point. And if we do that, now we ask the question, well, if we started right here and we ended at the same place, well, what's the potential difference between the same location? Well, it's 0. So let's clean this up a little bit. Didn't want to do all that. So let's see if we can put Kirchhoff's law to the test for a smaller circuit. So let's go back to the two resistor system, resistor A, resistor B, and a battery. We said we were going to start calling that E for EMF. So for this little side example, we'll say we have 10 volts. Resistor A is 5 ohms, resistor B is 15 ohms. Now we can go through this and we can solve for the current, but at this point I really don't need to. With Kirchhoff's law, we have some steps that we need to follow if we want this definition to work out to our advantage. And so the first law, or not the first law, the first rule of Kirchhoff's law is choose a starting point. Okay, we want to start somewhere in this circuit, and it really doesn't matter where we start, just as long as we're somewhere on that closed path that we want to follow. In this case, we don't have a choice. It's a single loop. But I'm going to go ahead and pick this point right here as my starting point. And we're going to label that point V sub A. That's our starting point. Now that A right there, I should probably say now it has nothing to do with that A. They're different. In fact, let's just so we don't confuse anyone, we'll just call those resistors 1 and 2. Okay, so VA is just a completely random point on the circuit that we start our summation from. Step 2 for the rules is choose your path. Now, there may not seem like there's a whole lot of choice in going around one loop, but there is. We could go around this loop in a clockwise fashion or a counterclockwise fashion. And depending on the direction that we go is going to have an effect on how we put together these equations. In more complex circuits up here, choosing your path does in fact make a great difference, because I could go through the left-hand loop, I could go through the right-hand loop, I could travel around the outer perimeter. So there's actually 3 different paths that I could choose from this top picture, but we'll come back to that. So choose your path, and I like to put 2 little side notes down here. When you choose your path, something you want to consider: do you want to go with the current, or do you want to go against the current? Because depending on which way you travel around this loop, you're either going to be traveling in the direction of the current or opposite the direction of the current. Okay, so it's an important distinction that we know what's happening. So let's ask ourselves, which way is the current going in this loop? We already know that our EMF is the source of electric charge. The larger plate of our battery symbol, that's where we get our positive charge from. And so our current will have to travel in the clockwise direction. And in a number of different circuits books or electrical engineering, typically what you'll see is the current will be drawn in sort of a semicircle or circular shape here, indicating the direction of the flow. Alright, so I know the current is going to be flowing in a clockwise direction for this example. And my personal preference is that I usually just go with the current. So I'm going to travel in the clockwise direction. So I'm going to go this way through resistor 1, through resistor 2, and then through the EMF until I get back to that original starting point. Step 3 of our rules. Begin summation of potentials. Starting with V sub A. And I'll go ahead and bring us over here so that I have some more room and we can still see the circuit. So I start at VA. In fact, let's go ahead and label this VA. I start at VA, and then we travel along until we get to resistor 1. When I pass through resistor 1 with my current, Ohm's law says V equals IR. So whatever my current is times the resistance value of resistor 1 will be the potential associated with resistor 1. Now, we've been using Ohm's law for a couple of weeks now, and one thing that we have yet to discuss is, well, if we go from one side of the resistor to another, is this potential difference an increase in potential or a decrease in potential? And the way to answer that is keep in mind what a resistor does. A resistor resists the flow of charge. So if I have some, I wanted that to be blue. If I have some current that is trying to pass through this resistor, that resistance is going to slow us down. In other words, the potential at the initial entrance of the resistor will be greater than the final potential after we've passed through the resistor. So if we travel with the current, we will see a drop in potential for that resistor. And this is why I said that it was so important to know if we were traveling around the loop, going in the direction of the current or against the direction of the current. Because now we have a little side note to put in here. If we do in fact go with the current, then potential drops through resistors. However, if we do the opposite, our potential will increase. So if we're traveling through the circuit and we pass through a resistor, but we're going against the flow of current, let's see here, resistors are supposed to resist, but we're going against the flow of current. That's almost like a double negative, but what do you get with a double negative? well, you get a positive. In other words, the potential rises if we pass through a resistor against the current. Okay, well, what are we doing? Well, we're traveling along, and well, looks like we're traveling through resistor 1 in the direction that the current is flowing. So we will see a drop in potential. Whatever the potential is for resistor 1, we're actually going to see a drop in that potential value. Then we pass through resistor 2, again going with the current, and so there will be another drop in potential. Next, we travel along until we get to the EMF. And remember, our goal is that we have to go all the way back to the original starting point. So now we have to pass through the battery. So what happens when you pass through the battery? Well, there's a third little side note that we're going to take here, and we're going to look back up at our picture. We started by entering the battery on the negative side, and we exited on the positive side. So we went from a negative potential to a positive potential. And that means that the difference going from a negative to a positive, our potential is becoming more positive. So we're going to see an increase in potential when we pass through that battery. Now here's the easiest way that I have learned that helps me to remember what kind of sign notation you get when you're passing through a battery. And that is the sign on the emerging plate equals the sign on the potential difference. Potential difference of the EMF. So what happened up here when we passed through that battery? Clean this up so we can see better. What happened when we passed through that battery? Well, I emerged on the positive plate of the battery. So we had a positive increase in potential. Well, there's the summation of everything in that circuit, and we are now back at the original starting point. And because we're back at the original starting point, that means that everything that we just added up has to equal VA. And you're like, well, wait a minute. You said with Kirchhoff's law, the summation has to equal 0. Well, this is why we started at this random starting point VA, because what we can do now is we can subtract VA from each side, because what is the potential difference between VA and VA? It's 0. And that's exactly what we've accomplished by going around in that closed loop. So everything that's left, we have negative V1 minus V2 plus E1 equals 0. that is the equation that we have for this miniature little resistor picture. So we're going to take that equation, we'll bring it up here, and I'm going to apply Ohm's law to the two potential expressions. We have the negative V1, but what's V1? It's the current times resistor 1. So there's V1. Then I have minus V2. Well, what's V2? V2 would be the current that passes through R2. And then we have the addition of the EMF, and all that equals 0. So this is the same equation as what we put together here, only now I have the unknown current value showing up. And I really don't like those minus signs on those two front terms. So I'm going to add them over to the other side. And when I do that, there's a little bit of cleanup that we can do in this expression. I'm going to factor out I. And then, well, I know what the value of the EMF is. I've been calling this EMF 1, even though there's only one EMF in the circuit. But I know what the value of that EMF is. I also know what the individual values of the resistors are. And so I can find the current. We have an EMF of 10 volts, and we have R1 plus R2, that makes 20. So we're getting half an amp for the current running through this circuit. And when I first drew this circuit over here, you were probably saying to yourself, "Oh, that would be a really simple series circuit. I could make an equivalent resistor out of that, and it wouldn't have taken me nearly as much time as what we're doing here with Kirchhoff's law." And well, that's exactly what happened, because with series resistors, how do you get an equivalent resistance? Well, you just add the resistors together. And so we quite literally reproduced the series equivalent resistance example. But as we said about 20 minutes ago, equivalent resistance is not going to work on this circuit. But I can use Kirchhoff's law. I can use Kirchhoff's law to go around each of these loops and add up the potentials. And because I have two loops, I'm not going to have just one equation, but I'm going to produce two equations. So let's see what happens when we try to apply Kirchhoff's law to this circuit. And so let's see how we want to do this. We'll have to, actually I will erase a bunch of the stuff up top here because we don't need that anymore. We can use that as some of our workspace. Rid of the wheel. Okay. Now, as you can see, for that left-hand loop, I drew the current going in a clockwise fashion, and that's because, well, I know where positive charge is going to come out of that first EMF. I also know that positive charge is going to come out of this second EMF, and so the direction that that charge has to flow is probably going to look more like a counterclockwise example. And I'm going to label these current 1 and current 2. And that has nothing to do with resistor 1 or resistor 2. I'm just using these to distinguish between the two currents. So I have current 1, which is going to flow through resistor 1. It's going to flow through resistor 2, and it's going to flow through resistor 3. I have current 2, which will flow through resistor 4, resistor 2, and resistor 5. Now, can you have two currents running through the same resistor? I've used a lot of water analogies in previous discussions, so I'm going to try one here. Current, it's a flow. So think about water flowing through a hose. Could you take two garden hoses that were connected to two different faucets and connect the two faucets together to have their combined water flow through a single hose? And well, there's no reason you couldn't do that. I don't know why you'd want to, but you can do it. And we can do that with circuits as well. So it is possible to have more than one current passing through a resistor. So sometimes the resistor just has to share the space with more than one current. As long as we can make our equations, we're good to go. So I'm going to make an equation for the left-hand loop of our circuit and one for the right-hand loop of our circuit. So Kirchhoff's law says, step 1, choose a starting point. So on our left-hand loop here, I've got multiple locations that I could choose for where I want to start, but I'll go ahead and keeps happening. Alright, I guess I should stop doing that. But I'm kind of a creature of habit. I typically like to start right above the EMF. And we label that as VA. That's our random starting point. Get rid of that stuff. Step 2 of our rules is choose your path. So, do I want to go with the current or against the current? And again, I am a creature of habit. I'm going to go with the current, so I'm going to travel in a clockwise fashion through that left-hand loop. And that means every time I pass through a resistor, I'm going with current 1. And we had that little side note. You know, it does depend on which way you're traveling, if you're going with or against your current. If I'm going with the current, then every time I pass through a resistor, I see a drop in potential. And I'm just erasing some more stuff here so it doesn't get in our way. And now we're ready to go. So we start at our random starting point, VA. We pass through resistor 1 going with the current. And I'm going to go ahead and just jump right ahead. The potential difference across resistor 1. We have current 1 going through resistor 1, so that will tell me what the potential of V1 is. And then I substituted that into our equation. And remember, it has to be negative, because we are experiencing a potential drop. Next, we turn, we pass through resistor 2, going with current 1. So that's another drop in potential. But what else is happening when we pass through resistor 2? Resistor 2 doesn't have just current 1 passing through it. It also has current 2 passing through it. As we pass through resistor 2, we are traveling in the direction of current 2. And so there's going to be a potential drop as a result of that. After we get through resistor 2, then we travel through resistor 3, going with the current. And this is just current 1. And then finally, we pass through our EMF. And as we pass through the EMF, we emerge on the positive plate, which means we increase our potential in the amount of E1. And now we're back to our original starting point, VA. And again, even though I don't know what the potential value is at point A, I don't need to know because they cancel out of the expression. And now Kirchhoff's law is satisfied. Everything on that loop has now added up to equal 0. And again, I don't like all those minus signs. I could add all of those current terms over to the other side of the expression, and then I would get something that looks like this. Here, I like that better. So all the potential differences that we encounter passing through those resistors now have to add up to what we have for the battery, and that's actually something that we're a bit more familiar with in our work. Okay, well, I know what all the resistor values are. I know what EMF 1 is, but I don't know what either of those current values are. So we have one equation with two unknowns. That's not a good situation to be in. So what do? We go get more information. We make another equation. And that equation is going to come from the right-hand loop. So for the right-hand loop, clean this up again. For the right-hand loop, starting with Kirchhoff's law, we need to choose a starting point, and that starting point has to be somewhere on the closed loop that we're going to be traveling on. If you notice, VA is not on that right-hand loop anywhere. But that's okay, I can pick another point, maybe this point, as my starting point. But I probably don't want to call it VA, that would get confusing. So how about if we call it VB instead? It really doesn't matter because that random starting point is just going to be thrown out anyways after we do our summation. Next step in Kirchhoff's law, choose your path. Well, my path is already chosen. I'm going to travel around the right-hand loop, and I will choose to travel with the current. I will follow I2. So I'm going to travel through resistor 4, resistor 2, and resistor 5, all the way traveling with the current. So we'll start our summation starting at VB. I pass through resistor 4 with current 2, that is a drop in potential. I then pass through resistor 2 with current 2 and with current 1. So just like the above equation, I have to take into account both of those currents as they travel through resistor 2. And then we pass through resistor 5, going with the current. And lastly, we have to pass through EMF 2, emerging on the positive plate. And that gets us back to VB, which we don't need to know because it's going to cancel out. And we have our second loop equation. And again, I don't like all those minus signs, so I'm going to go ahead and move all of those current terms over to the other side of the equality. And we'll do this quick little shuffle again. Plus, 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 plus. So now we have two equations with two unknowns. I know what all the resistor values are, I know what the battery values are, and you'll notice we haven't even touched the table. This was kind of going on the impression that we were going to use the equivalent resistor approach, so I guess that was a bit of a misleading step there, but at this point we have two equations with two unknowns, and we can solve for those two unknowns current values. And the minute we do that, we can use Ohm's law on any of the resistors in that circuit, because all five of those resistors are going to have either current 1, current 2, or said combination passing through them. And I can use that to find the potential difference across any of those resistors. So this video is getting a little bit long, but please bear with me. We need to finish this. If you need to pause, take a break, go for it. I'm just going to go ahead and complete the problem, and to do that we need to solve our system of simultaneous equations. To do that, I would like to make my life easier, and to do that I'm going to clean up this system of equations as much as I possibly can. For that top equation, I have a lot of terms with current 1 in them, so I'm going to factor out current 1, which will leave me with R1 plus R2 plus R3, and then we have that single I2 term equals E1. Likewise, for the bottom equation, there are a lot of terms that have I2, so I will factor those out. R5 plus the I1 term. And you might be thinking, well, that doesn't look all that much better, except now I'm going to come back to the values of those resistors. Like I said, I want to make my life easier at this point. So let's just put in the resistor values. For the top equation, we have I1 times the combination of resistors 1, 2, and 3. And let's see, 45 and 15 is 60, plus 20 is 80. And then we have I2 times R2, which is 20. equals, and I'll even sneak in the value of E1, which was 100. Alright, so there's our first equation, looking much better. The bottom equation, I2 times the combination of R4, R2, R5. That gives us, let's see, 20 and 30 and 5 is 55. I1 is 15, and then E2 was 50. And there's our second equation. Now, if you wanted, you could even reduce these down further. Every term in this top equation we can divide out 20. Looks like we've got, yeah, 20. 20 is the greatest common denominator of all of those terms. So we get 4 times I1 plus, whoops, that's not right, I1 plus 1 times I2 equals 5. Oh, so this is starting to look better all the time. And then this bottom equation here, let's see, at the very least I could factor out a 5 from everything. So we would get 11I2 plus 3I1 equals 10. And then I'll put these right next to each other. And I'm gonna swap the terms around so that I have I1s and I2s in line with one another. Still equals 10. And this is our system of equations that we have to solve now. So that's not looking too bad. This is something that we learned to do in algebra. We did this a couple of times in Physics 1. Probably the best way to solve a system like this is to use the common multiple combination approach. So what I'm going to do is I'm going to take that top equation and I'll multiply both sides by 11. And you might be thinking, well, where the hell is he getting 11 from? Well, 11 times 1 would equal 11. And then if I subtract the two equations from each other, I'll be able to eliminate the I2 term, leaving me with an equation that's only which only has one variable remaining, which is I1. So multiplying 11 through that whole first equation gives me 44I1 plus 11I2 equals 55. And I'm going to subtract the bottom equation from that. Because if I take 11 I2s and subtract 11 I2s, those are gone. I just have to be careful with all the other algebra that we're doing here. 44 minus 3 is 41. 55 minus 10 is 45. And so I1 is going to equal 45 over 41. Which is not a very clean outcome, but this is what happens when you make up the numbers on the fly. I just made up all these values here, but there's no reason why the algebra shouldn't be able to tell us what our answer is. So 45 divided by 41 equals, and I'm getting 1.0975, so I'm just going to round that up to 1.1 amps. And now if you wanted to, you could take your answer for I1, plug it in, and solve for I2. But what if I got I1 wrong? If I1 is wrong, then I2 is going to be wrong. But we were able to solve for I1 independent of I2, so we should be able to go back and solve for I2 independent of I1. And the way I'm going to do that, let's see, we were able to eliminate I2 by finding a common multiple. So I need to find a common multiple for the I1 terms, and that is 12. And that means I will have to multiply the top and bottom by 3 and 4 respectively. I'm going to bring my work down here. The top equation becomes 12I1 plus 3I2 equals 15. Bottom equation becomes 12I1 plus 44I2 equals 40. So I now have the same scalar coefficients on the I1 terms. I will once again subtract the bottom equation. 12I1 minus 12I1 is 0. 3I2 minus 44 is a negative 41I2. And then we have 15 minus 40, which is a negative 25. And so I2 has to equal negative 25 over negative 41. That's going to come out to be positive. And I'm getting 0.61 amps. Now this is probably a good place to mention, is it possible that you could go through all of this math and get a negative current? And the answer is yes. For some circuits, it may not be as intuitive to us as to which way the current is going to be flowing, because we can get some pretty complex circuits out there and we may not know which way the current is flowing. But don't let that stop you. If you don't know which way the current is flowing, just pick a direction and go with it. And if you guess the wrong direction for the flow of your current, the only thing that's going to happen is when you solve for that current, you'll get a minus sign. Not the end of the world. Okay, so we've got our two current values. Are we done? Kinda. But now it's time to check our work. So where's our self-check? Well, there's two of them right up there. Our self-check says that 4 times the value of current 1 plus 1 times the value of current 2 must equal 5. So let's check that. We have 4 times 1.1, which is 4.4, plus 1 times 0.6, which is 0.6, which gives us 5.01. Well, that 0.01 there, that's to be expected from some rounding error, but I'm okay with that because we're getting a true statement out of the first equation. Let's try the second equation. 3 times the value of current 1 plus 11 times the value of current 2 has to equal 10. 3 times 1.1 is 3.3 plus 11 times 0.61 is 6.71, and if we add all that up, we get 10.01. Again, a little bit of a rounding error there, but I think Wiley will accept that. Okay, so we're done. We found the current running through either side of this circuit. We did not have to use the, come on, I need my eraser. We did not have to use the equivalent resistor approach, not because we didn't want to, but because we couldn't. We didn't actually have a system here with resistors connected in series and parallel that we could take advantage of that approach. But Kirchhoff's law did allow us to find the values of the currents in those two loops. Sorry, that's current one. In the future, and this is not something that I would expect you to do for a homework problem or a test problem, but you could end up with circuits that have more than two loops. And I'm being very sloppy here with my drawings, but you know, what would you do if you encountered a circuit that had multiple loops like this? And the answer is, well, you would apply Kirchhoff's law to each individual loop. Again, we may not know exactly what direction each of these currents is flowing. We're just going to give it our best guess. For these top three, I would be pretty confident in saying that those are probably the directions of the current flow, just because of the way the batteries are set up. But what about this this fourth loop down here? Well, I have no idea, but maybe I just, whoops, screen shifted over for some reason. Maybe I just go with this direction. What does this mean for us? Well, it means that you're going to have to produce 4 equations. One for the first loop, one for the second loop, the third loop, and the fourth loop. And because you're producing 4 equations, technically you could end up with a system of 4 equations with 4 unknowns. But that doesn't mean that it's impossible. It can still be solved. It's gonna take quite a bit more time and effort than what we had up here, but it can be done. And it's probably better done on a calculator or some other software system, maybe on a computer. Once you set up the equations, which really isn't all that complicated of a matter now that we know how the rules of Kirchhoff's law need to be followed, we could very easily go through this diagram, and if we actually introduced values for all of these resistors, we could very quickly come up with equations for each of these loops. The problem is that I don't want to solve those systems of equations, so in that case we would let a computer do it. Alright, so that is the example for multiple loops. Keep in mind, at this point your book is going to stop using V for all the batteries. You're going to start seeing E for EMF, but we're going to treat it exactly the same way that we have been with all of our other circuit problems. We're going to have one more video on the Chapter 27 material, and that is going to cover what we call RC circuits. And these are circuits that involve both resistors and capacitors in the same circuit. And so we need to see how we combine the material from this chapter relating to the resistors to the chapter 25 material that dealt with capacitors. And we want to see what kind of equations Kirchhoff's law will produce for us then. So thanks for sticking through this. I know this was kind of a long and complicated example problem, but just like the equivalent resistor equations, take your time, draw everything out, write everything out, be as detailed as possible, because at some point you're going to have to come back and revisit some of the stuff that you've written down. Okay, have a good one. See you at the next video.